Good afternoon. My name is Fabrizio Ferrandi. I'm an associate professor at Politecnico Milano, and I'm going to present Bambu in this EVEREST webinar. The presentation is actually organized in this way. So we have on the left of the screen a set of slides. On the right of the screen, we have a Python notebook. In this Python notebook, we are going to demonstrate the high-level synthesis Bambu I'm going to present. So the first things that we need to do, since it takes a while, is to install all the file required and the app image binary distribution of the Bambu tool. The app image is a file including a compiler and the high-level synthesis tool Bambu. So let's start this installation, this setup, and in the meantime, we start with the webinar. Okay, so a bit of history about Panda. Panda is a framework we have set up quite a long time ago in 2004. It has been set up in order to support the research we do at Politecnico Milan, and it has been used in several projects, starting from the iCodes project in FP6 framework till today to the EVEREST project in H2020 EU-funded project. This webinar is meant as a sort of dissemination of the activity for the EVEREST project. The framework was used for many different purposes, for supporting the analysis of system C description, the extraction of parallelism, the estimation of the performance for embedded application, and the high-level synthesis. And today we are going to focus the presentation mainly on the high-level synthesis stuff. Then, what is Bambu? Bambu is an example of HLS tools. It's an open source tool. It could be is distributed by means of the GitHub website. All the sources are there. You just need to have a Linux machine and compile that object on that on your stuff. Or you may actually use the binary distribution I mentioned before, so the app image binary distribution. These tools is, as it happened for many HLS tools, is going to have a front end, and the front end is based on standard compiler like GCC and Clang, and is going to support the full set of ANSYS, mainly because this is managed by these compilers. In this way, we are actually able to exploit all the code optimization done by these tools. So all the optimization implemented in these tools could be exploited by Bambu in order to generate the most efficient hardware possible. It's an high-level synthesis tool, and the results depend on the target device considered. This is done through a characterization of the IP library exploited by the tool. It is possible to verify and co-simulate the design generated by exploiting open source tool like iVerilog or Verilator, or commercial tool provided by the different provider like ModelSim, iSim, XSim from Xilinx. It is integrated with existing backend, both for FPGA devices and ASIC devices. In particular, we are able to support synthesis towards ASIC device by exploiting OpenRoad project. And for the FPGA, we support both Xilinx, Altera, Lattice, and non-explorer device technologies. So, as a high-level synthesis, many high-level synthesis tool, you have three different parts. in which the tool is split. The first part is the front end. So as I said before, Bambu is integrated with GCC and LLVM. Mainly this is done by extracting the intermediate representation of this compiler and translating in a single format and then read back by Bambu tool. In this way, we are actually able to extract some annotation from the initial specification, and in this way, this annotation will be passed to the rest of the high-level synthesis tool. So at the end of the front end, you are going to have an intermediate representation over which the tool is going to work. Besides the standard optimization implemented in GCC and LLVM, we implemented many other transformation and optimization done at the middle end phase, like transformation of the arithmetics, the analysis of the bit width of the variables and range values. All those kind of things are very important in hardware in order to reduce as much as possible the hardware used. And plus, since this kind of transformation may actually activate the other possible transformation, we integrated some other existing transformation in order to reduce as much as possible the size of the device, such as the rewriting of some simple expression in lookup tables, such as the constant propagation, such as the dead code elimination. All these kind of things are actually very focused on the hardware target device that Bambu consider. After the middle end, we may start the standard step you usually followed in high-level synthesis. So you have the scheduling, the register and functional unit binding, and the resource allocation, and all these kind of things are ending up in the building of an FSMD hardware template. And starting from this internal description, we are going to generate the description that could be synthesized and verified by external tools. In addition to these steps, we have some specific steps that are specific to Bambu, like the memory allocation, the function allocation, and some steps that are used in order to verify the correctness of the output generated, and somehow that try to understand where possible bugs are inserted in this design flow. As I said before, Bambu, it's a command line tool. So the most simple command that you may have is just calling the Bambu, passing the file name of the C file that you would like to synthesize. You may pass additional option like the top function name, like the clock period, and like the device. Let me show you how this kind of things works on the Colab stuff. So we have installed the app image, so the Bambu tool. So now we have the Bambu over this remote machine provided by Google. So we may run the tools just in order to get back the help of the tools. So once we have done this, we may actually do some more interesting things. So we move to the first example, and the first example are related to the synthesis of this very simple function that computed the CRC over this input data. So you have a loop, and then you have a returning values. So in order to synthesize this, you just need to pass the C file, specify the top function name, the simulator used, and the input stimulus. And this input stimulus are the one that will be passed to this function and to the component generated by Bambu. So here you are going, let me show you this XML file in order to understand the complexity. So let me run this. Okay. So here is the synthesis of the tools, and here you are going to have the number of cycles taken by this this simulation. And here you're going to see the XML file used in order to, just a second. The XML file used in order to stimulate the component and the C file. And here you are going not this way. Okay. Okay. So the stimulus is taking these signals, these values to the parameter, and these are passed to the C file, simulated, and then computed the return values of the function. And the similar things is done on the Verilog component. And these two values are generating these two results. And since they are the same, we assume that the C and the Verilog component are going to have the same behavior. Here you are going to see other files that are generated by Bambu. So for example, this is the file the script file generated by Bambu in order to perform the very later simulation. And this is the synthesis script targeting the Vivado for this example. And then you have other intermediate file that could be useful in order to understand what is done by the Bambu high-level synthesis tool. So, for example, this is the dump of the intermediate representation written in C, and this file could be compiled and simulated in order to see the exact behavior. And it is used sometimes to perform to verify the correctness of the final results. In addition to this intermediate file, you may see some other generated file. Let me show you the dot file for the FSM, but there are many other. So in this dot file, you are going to see the FSM generated for this very simple component. I mean, here we have the loop in this state, and this is very related to the 4 we have seen before for the CSC. And this is going to take 1 cycle there, 8 cycles there, and 1 cycle there, in a total of 10 cycles. Okay, fine. So we have seen how the Bambu tool works. So let's go back to the presentation. So the high-level synthesis tool, since it's based on Clang LLVM and GCC, is actually able to support mostly all the C, C++ input. It is able to synthesize many things, including some strange dynamic pointer or analyze memory access or GCC vectorization. The only things that is not supported very well by Bambu are actually 2 things. One thing is the structure returned by copy, but this could be somehow sorted out by just rewriting the code and returning the values through by passing the pointer to that struct. And the other things is actually much more complex to solve, since Bambu is not able to synthesize recursive function, but not all the recursive functions that are non-tailing recursive. Because if the function is tailing recursive, the compiler like GCC and Clang are actually able to convert in an iterative way. Bambu is not only translating the code provided by the user, but is actually able to synthesize many libc and libm function. For some of this library function, we have developed a specialized version for the hardware synthesis. So, for example, all the trigonometric and all the exp and log function have been somehow designed in order to be the most efficient one you may have for the hardware target. The next example I would like to show in order to present the feature of this tool is about the synthesis of specification with complex pointers management. And in order to show this, we take a very simple example dealing with a binary tree. And in order to traverse this binary tree, we use a stack somehow to show that, I mean, even if this is not supported the recursion, you may actually convert a recursive function in a non-recursive way by introducing an explicit stack. Since the dynamic memory allocation is not very efficient with hardware, we have implemented this with a static memory allocator. And the functions that you are going to see are recursive, but they are tail recursive, so the compiler are actually able to synthesize all of them. So let's open the example. So the example is this tree. So here you may see that the function implemented are somehow common C code, and so not very specific to the hardware. So, and as I mentioned before, we have a static pool tree and a tree list that we will use to manage the stack and the binary tree. And then we have a main at the end of the file where we build a tree, and then we traverse this tree in pre-order, in order, and post-order. And this visit is done by exploiting the stack data structure I mentioned before. Another interesting thing is about these two functions, so this built-in Bambu time start and the built-in Bambu time stop. These two functions are used in order to profile the time taken by the search function. And this is done twice, so one in this point and one in this point. So now let me run this example. So at the end, does not take too much. Here is the summary. So here you are actually see the print on the screen. This is actually just simulated. So the printf are actually converted in display in Verilog. In the total number of cycles for the main is 2,705. But here is reported the total number of cycles spent in the two calls of the search, so here and here. And here you have the number of time that you do this profiling, and here you have the average execution time. If you inspect the file generated, intermediate file generated by Bambu, you may actually see other kind of things. So here you have the script and it's very similar to the one we have already seen before, but this one is much more interesting because it's actually a fine collection of a fine-grained collection of time. So 2 means start, 3 means T3 means the end of the function. So if you do the difference between these two numbers, you are going to have the exact number of cycles for the first search. The same way the total number of cycles for the second search. So you may actually have a very fine-grained profiling of the function by performing the simulation of the Verilog with the instrumented code. Okay, fine. So we have shown that pointers are not a big problem for Bambu. So let's move ahead. So as you have understood, the synthesis is done per function. Each function is converted in a component. Each component is going to have a start and done, and is going to have a set of parameters. So if we go back, for example, in the previous examples, the hardware generated this one. So let me go a bit up. The Verilog is an hierarchical Verilog, and the Verilog is going to have more or less the same, always the same structure. So you all are going to have always clock, reset, and start port. And then you have the parameter for the function, and then you have the done in order to assert the completion of the execution, and you have the return port for in case you have returning values for the function. You may specify for the some of the parameters some other protocols. So you may have a parameter working as a FIFO or working as an array, as it happened for other commercial tool. And you may have a memory bus in case the function is going to access external memory. The organization of this file follows more or less the call graph in the function, and you may not have recursion, so you are not having any cycle in this call graph, but you may share some of the component in the hierarchy. Okay. So another thing that I would like to show in this webinar is related, let me close this point, is how to use the Bambu high-level synthesis tool in order to synthesize a file generated by a Clang compiler. So it is possible to synthesize directly the intermediate representation used by Clang by starting by the .ll. In this example we have, so let me close this. In this example we have a C file. In the script we are going to generate the .ll file by passing these two options at Clang 12. And then we call Bambu by passing exactly the .ll. So we use a standard Clang 12 compiler. We pass all the optimization we wish, and then we pass this this .ll file, so the intermediate representation used by Clang, directly to Bambu. And we do the same thing. So we pass all the same parameter we passed before. So the top function name, the clock period, the type of device we apply to, the stimulus, the name of the compiler, and we generate some intermediate file for about written in C for the intermediate representation. Okay, let's run. So Bambu is not working on the C file, but is working on directly on the .ll file. So the final result is 123 cycles. So it works exactly as we pass a C files. The nice property about this example is that it's a crypto core, and it's been ended Clang 12, and so the recent compiler are actually able to optimize quite well this example. And so you are actually able to reach very high throughput for this kind of design. So since it's going to process 1,600 bits, and this is done in 123 cycle at 400 megahertz. So this means that we are able to reach a throughput of 5,200 megabits per second. These are previous results that give an idea of what can be done, changing the target technology and changing the compiler. Okay, now, so we have seen that it's possible to start from .ll. Another thing that is I would like to show is the fact that Bambu is not only working on the C, C++ intermediate representation, but is actually able to integrate a file written in Verilog VHDL and the synthesis of the system. And so you may see in the source distribution of the code that you are able to combine part in Verilog and part in C, and all these kind of things may be combined in a bitstream that could be uploaded in existing FPGA. Another thing that is supported by Bambu is the synthesis of pointer. Here you have an example where you have different filter, and this filter are actually passed to the execute as a pointer to function. And Bambu is actually able to synthesize even pointer to function. Another thing that the Bambu is actually able to perform is to synthesize starting from C++. So templates are not a problem. C++ 11 is not a problem. We are actually able to synthesize even description in C++, 17, 20. Anything that is supported by Clang or GCC could be supported by Bambu. Another interesting things about C++ are the libraries that are have been used in the current commercial tool, like Mentor Graphics Tools for HLS and Xilinx and VT's HLS for Xilinx, in order to describe hardware type. And so it is possible to, even in Bambu, to have a code that is described using AP types or AC types. And here we have an example of this. So here we have an example, and we have the greatest common divider, but the data passed to this greatest common divider is passed using AP int with 11 bits, and the parameters are taken from outside by following the FIFO protocol. So you have two input FIFO and one output FIFO. And so here you're reading the data, and here you're writing the data. And this is an infinite loop. And here you have some pragma that describe the fact that these three parameters are actually following this specific protocol. So Bambu is actually able to understand this. And we may run the synthesis. Let me close this. So this is being almost done. Okay, 6 cycles. So the output is this one. And as you may see here, you have clock reset, stop port, dump port, but you have all the signals required in order to manage input FIFO and output FIFO. Okay, fine. So we have showed this. Go back to the presentation. The next thing I would like to show you, let me close some of the things. It's about the MLIR synthesis. So the idea is to show that it's possible, starting from an MLIR affine dialect, to perform the high-level synthesis. MLIR is something that have been introduced by the Clang community, the LLVM community, in order to describe application for machine learning, or actually for linear algebra in general, in order to raise the level of the abstraction. And here we have an example, a very simple example, performing the matrix multiplication. So here is the description of a matrix multiplication performing this computation. This is described using the affine dialect. So let me prepare the directory. Let me write the file in this directory. Now, in order to perform the synthesis, we need to translate this affine dialect in something that could be understood by Bambu. And so this is done by converting this in LLVM-IR. And this is done by using standard MLIR opt and MLIR translate. So here is the results of the translation. And so as you may see, it's a standard LLVM description. Once we have done this, we need to prepare the stimulus file, so the test bench file that is an XML file. And since we have 32 times 32 array as input, as a input for C, A, and B, here we are going to have 3 different parameters and 3 different initialization of this. So here we are going to have 1024 input elements. So these are going to be passed to Bambu, and here is the line of code that perform the actual synthesis. So again, here I'm passing the .ll file, and so I'm running this. So let's see what happened there. And here at the end, we are going to have the synthesis of this representation. And the final results, it's about almost 400,000 cycles for this. Another things that could be done by passing some option to Bambu is to change the floating point type using this by the synthesis. So instead of using the single precision floating point type using this example, we are going to say, okay, fine, the floating point operation are not using this this kind of single precision, but we would like to have with passing some this string, we would like to perform all the floating point computation by exploiting the half precision data type. So 8-bit for the exponent and 7-bit for the mantissa. What is usually this is named B float type. And then Bambu is actually able to perform all the adaptation and customization of the computation. Obviously, the results will not be exactly the same we have with single precision, but in some condition we may accept some approximation of the results, provided that we have some benefit in terms of results in terms of area or in terms of number of cycles. So by passing from the single precision to the half precision, we have quite a good speed up, and so we are able to improve and reduce the number of cycles. And here I'm not going to do any synthesis, but as well we are going to have less area. And this gives you an idea how this some sort of design space exploration could be done easily by the high-level synthesis Bambu. Okay, go back to the next slide. So the next things I would like to show you is about another feature of Bambu. And this is related to the support of SIMD vectorization. In particular, Bambu, besides supporting the standard vectorization done by GCC, is actually able to, in Bambu, there is some steps that are able to perform outer loop vectorization. Here you have an example of what this kind of transformation is actually able to do. So here you have the standard, you have two nested loops. These two nested loops are having a dual type of parallelisms for the outer loop. So it is possible to run two iterations of the outer loop in parallel, and Bambu is actually able to merge these two iterations in a single one. And so you may actually parallelize these in this way. And here you have the input code that is supported by Bambu. Here we have an example in the Colab environment. Let me close this. So here you have the, let me see, here you have the outer loop. Here you have the function where you have the inner loop. Bambu takes this with this annotation and understand that the outer loop could be parallelized. Now, the script, in order to perform the synthesis, this one. So here I'm just performing the synthesis without any parallelization. So the number of duplication of the outer loop are limited to 1. So no, this is actually performing the sequential synthesis. So let's do this first. And then we are going to parallelize 4 times the outer loop. So we are actually overlapping 4 iterations of the loop. So the number of cycle is this one. So let's change a bit the script by putting a 4 here and run the example. And at the end, you're going to have a number of cycles. Okay, fine. a number of cycle that is giving you a speed up with respect to the beginning of 2.93. Not bad. Okay, fine. So this is about the SIMD. There is another thing that Bambu is actually able to do. We have developed an initial support of OpenMP parallel 4. This has been done in order to somehow exploit coarse-grained parallelism for some code that perform synthesis for a database, graph-based database. And the idea is this has been done by somehow customizing the memory subsystem and somehow replicating the kernel that could run the given information. So here you have an example. So this OpenMP parallel 4 means that you're going to have for this kernel many possible different instances that could run in parallel. Here you may have a variable degree of this kernel, so this is pretty dynamic. So let me close the previous example and let me show you what happened in this specific synthesis case. Just a second. So close the SIMD, open the OpenMP. So here we have the full query. So here you have the kernel, here you have the parallel code where you have the OpenMP4, and here you have the top function performing the search, and here you are going to have the test function loading all the stuff and so on and so forth. And so let me show you the script. So the first script is meant for sequential access. So we are not performing any parallelization. So the number of threads is equal to 1. And we perform the simulation in order to see how long it takes for the sequential case. And takes a bit, but not so much. I mean, here for the webinar, which was a simple example, but not so much. I mean, they are complex in other perspectives. So here we get the simulation, and the simulation ends in this number of cycles. Okay. Now we consider another possible case where we specify that we have two physical copies of the kernel function. So the number of threads is equal to 2. And we introduce and we connect these two kernels to an external memory with 4 banks and 2 channels. And we have that for each of these kernel, we have 4 possible context switch. So this technology is actually able to not only parallelize the kernel, but is actually able to suspend and perform the context switch on the same kernel. And then we run. And so even if we have 2 components, but these 2 components are actually able to suspend and resume, we are actually able to speed up the computation as expected, but more than 2. So we are actually able to have a speed up of 3.3, shown by this number of cycles. This is actually obtained by replicating the kernel, but even by supporting the 4 different context switch on the same component associated to each of the kernel. And so we are actually able to have a speed up in the order of 3.33. Okay, fine. So this is the webinar about the Bambu. I have presented some feature about the tool. Here you have some links to the website associated to the framework, the GitHub repository, and the link to the collab environment. In this way, you may actually play with Bambu without actually having to compile and install on your machine. You may just use Google Colab in order to do all the analysis. I think I am done. And let me stop the recording. Thank you very much for attending this webinar.